Welcome back to discussion 19. We're going to do problem number 44 from page 357. So we're given a situation where we have two support beams and there's a wooden plank resting on top. There's a person standing sort of near the end but not too far to the end. We want to know how far can this person walk out before it starts to tip at this point. So this person's going to walk out here, their weight force is going to push down here, and this torque is going to come up this way. So really we have a torque problem. We want to balance this torque with this torque, right? Right now, we can comfortably say that the torque headed in this direction balances out with the torque over in this direction here. We'll call this T1, and this is T2. So we can say that the net torque operating on this before, or at least right now at this point, is going to be T1 plus T2 is equal to 0, right? And now notice that we have to consider that these are going in, these are actually pushing in opposite directions, right? Because I drew the arrow up here to indicate that that's the direction it's going to go if the torque here is great enough. But to balance out, we need the torque here to balance with a torque this direction. So the weight force of the board is pushing down over here, and the weight force of the person is pushing down over here as well. Okay. So what does that mean? That means that we have negative T1 because we are going in an opposite direction. Negative T1 plus T2 is 0, or tau rather. So that means that tau 1 is equal to tau 2 in equilibrium. That makes sense. So now we're given that we have a weight force is equal to 100 newtons for the board. Okay, and then the weight force for the person is equal to 80 newtons. So here I've already written down torque is equal to R cross F. So what we would do is then we would take T1, R cross F is going to be 100 newtons for the board, right? For this board here. We need to consider that R for this side is actually going to be, so we have a weight force that's pushing down directly in the center of mass of this plank, right? So it's just pushing down this way. The torque, however, is pushing down over here, 4 meters from the fulcrum point. Okay, so we need to figure out what is the difference between those. This whole thing, we're told, is 6 meters in length. So something, a plank of a uniform density is going to have a center of mass directly in the center, because this is just a plank or a rod. So this gives you 6 over 2 is 3, right? So we need to take the difference. So we have 4 meters minus, what did I say, 3 meters. That's where the center of mass is. And that's going to equal T2. So now, writing this out, we would get, if you wanted to write it this way, we'd have F weight force, R, let's see, RCM, and R torque. Just to kind of give you a more vivid picture. Okay, so now we have 100 newtons. 4 minus 3 meters is equal to, what did we have here? We had this torque here is pushing at, we don't know exactly how far we can go in equilibrium. That's what we're trying to figure out. So now we want to go here, X equilibrium, we can call it R equilibrium, times the weight force. That's going to equal 80 newtons, right? So that's 80 newtons. Right? Well, here, let's just rewrite this, make it a little easier. So we have 100 over 80 is equal to R in equilibrium, which is going to be 5/4, which is going to be 1.25 meters. So that's how far you can walk out from this fulcrum point here. You can go 1.25 meters, 1.25 meters. So, okay, we've already walked out half a meter, so we need to figure out how much further can this person go, because that's what we're asked to figure out. how far to the right can the person walk before the plank begins to tip? So we've already figured out the total distance is 1.25 meters, but we want to know how far from where they're standing. So that's just simply 1.25 minus 5. That's going to equal 0.75 meters. That's how much further they can walk before this thing decides to flip up. Okay, next problem. So next problem, number 48. We're given a cross product and we're given magnitudes of the vectors, and we want to know what is the angle between the vectors. Well, recall from before we had the dot product identity. That was equal to AB cosine theta. Well, now we have cross product identity, which maybe you could guess is sine theta, AB sine theta. So pretty much all we got to do is take, this is 42, so let's see. We're told that 42 k hat, that is the that's the value of A cross B right now. Okay, and then we had, what was it? It was 12 times 7. Those are the magnitudes. Sine theta. So then we just take theta is equal to the arc sine of 42 over 12 times 7. And that gives us a value of 30 degrees. That's what I found. Okay, number 49. So now we're given a very similar problem, but this time we're told that the value for A cross B is negative 42. So A cross B is equal to negative 42 k hat. That's equal to 12 times 7 sine theta. Again, we just take the arc sine of negative 42 over 12 times 7. This gives us a value of, you guessed it, negative 30 degrees. That makes sense because this was in the opposite direction. So 30 degrees and negative 30. Those are the answers to those problems. Next problem, number 55. Okay, we're told that we have a disk, and on this disk there is a 100 Newton force applied to its outer edge at 2 different angles. We're given that the disk has a rotational inertia of 165 kilograms meters squared. So we're told that I is equal to 165 kilograms meters squared. We're told that the force is equal to 100 newtons. And we're told radius. The radius is 4.5 meters. Draw them both so I don't have to do it later. 4.5 meters. And then the first one is, the first force appears to be perfectly tangential to the disk. So this is a right angle, 100 newtons. So now let's think about what we have. We're asked to find the magnitude of the torque that's applied. So torque, again, torque is equal to R cross F, right? This is a cross product. We just did 2 problems with cross product identities where we can relate them to an angle, right? So that means we can also, instead of trying to figure out what this is, we can take the magnitude, which is 4.5 meters, times 100 newtons, times sine theta, which is, in this case, 90 degrees, right? So that gives us our value directly, and that puts us at 450 Newton meters. Right? We have newtons times meters. That's Newton meters. That's actually a unit of energy, or a joule. So that's the first case. So we just took the magnitudes, r cross f. Instead of doing an actual cross product here, we just took the vector angle identity and solved. We can do pretty much the same thing for the next part. This next one, we're told, is applied at an angle of 70 degrees. Okay, so now T2 or tau2 is going to equal, well, let's see what we have. 4.5 meters. Again, it's 100 Newton force. This time, we're looking at the angle between them. It's sine 70 degrees. Well, what does that equal? That equals 422.9 Newton meters. So notice that the force that's applied tangential to the disk is much greater. Well, I guess it's not much greater. It's greater than the force that's applied at an angle to the disk. So always applying a force tangential to the disk will probably give you the greater torque, right? So as you decrease this angle, you're going to have a smaller and smaller torque. I mean, that makes sense because if you're pushing this way, you can spin the disk. But if you're pushing this way, the disk is not spinning, so there's no torque. Okay, part B. Part C, rather. So we just did A, and here's B. And now we do part C. Part C is, assuming the force on the disk is constant, what is the magnitude of the angular acceleration applied to the disk in each case? Okay. Well, again, torque is r cross f, right? It's also, there's an identity here where we have moment of inertia times angular acceleration. So the thing we actually want to solve for is angular acceleration. So we found earlier that r cross f for, well, let's say for the first case, this was equal to 450 Newton meters. Okay, we also know that we were told earlier that the moment of inertia is 165 kilogram meter squared. So now all we got to do is take this down here, or if it were over here, I alpha, right? I alpha, take this over here. This is 165 kilogram meter squared. That gives you a value of 2.72 radians per second squared. Okay. And then for the second one, we had a value of 422.9 Newton meters, and then we just divide that by I, which is 165 kilogram meter squared, and that gives us a value of, let's do it down here, that gives us a value of 2.56 radians per second squared. So again, that makes sense. So for the first case, we have a higher angular acceleration than the second case. So if we push tangentially to the disk, we're going to spin it faster than if we push it sort of at an angle to the disk. Okay, part D. Which is the more effective way of spinning the disk? Describe which quantity you're using to determine effectiveness and why you chose that quantity. Well, okay, it's just like we just talked about for each case. As we were going, I'd kind of described this. You have a greater torque if you push tangentially to the disk. That's more effective. If your goal is to spin the disk, then that's what you want to do. Push this direction. If your goal is to not spin the disk and you just want to push on it, then push towards the radius. Next problem. So next problem, number 72. consider the disk in problem 71. The disk's outer rim has a given radius and a given F1. Find the magnitude of each torque exerted around the center of the disk. So in problem 71, that's really what we're looking at here. From what I understand, Dr. Wood is also going to go through this in lecture, but I'm going to go through it because I can't solve problem 72 without solving problem 71 first. So let's just call this 72. And there's an inner disk here. We are given some forces. So from the center here, we're told that there's a force this way. This is going to be F1. And this is this, oops, excuse me. With the horizontal, this is 45 degrees. We're given that information. Okay, we're told that there's a force 2 here. F2. That's obviously tangential to this inner disk. And then we are told that there's a force 1 that's, or force 3, excuse me, that's tangential to the outer disk. Okay. So we're also told that F3 is equal to 2 F2 and 2 F1. One more thing, we're told that this is a radius of R2, R over 2, and the total radius is R. Okay, we want to find for the magnitude of each torque exerted around the center of the disk in terms of R and F1. Fine, no problem. Okay, so we can start with, let's just look at torque number 3. So we have torque 3. So this is kind of small. Okay, so this is going to equal R cross F3. Right? Well, we know that it's tangential to the outer rim where radius is R. So we could also just call this, now we can just take the magnitudes times sine of the angle, whatever that angle happens to be. In this case, it looks like it's 90. So we have R F3 sine 90, which, by the way, F3 is equal to 2F1. We want this in terms of F1, so we have 2RF1. That's going to be the value of T3. Okay. Next torque. So R cross F2. So this force is pushing onto the center disk tangentially, right? And then the radius is R over 2, so it's coming out over here. We'll use purple. So we have R cross F, in this case, is R over 2. It's sine 90, right? So we have R over 2 times F2 times sine 90 again. Okay, well, we can plug all this stuff in. That gives us, by the way, 2F2 is 2F1, so F2 is equal to F1, so that gives you R over 2 F1. Decent. Okay, so next part, T3 is equal to R cross F, 1. Okay, so, well, in the diagram, we have this force is crossed with this radius. This radius is R, right? What else? That's it. So here we have R F1 sine 90, because we're crossing it. We're told in the problem that F1 and F3 are tangent to the outer rim of the disk. So F1 is tangent to the outer rim of the disk. So if this is tangent to the outer rim, R cross F sine of the angle, where this angle is going to be 90 degrees. Okay, so that just gives you a value of R F1. One thing I'd like to point out before moving on is that we do have, so F3 and F1 are tangential to the outer rim of the disk, but we need to notice that they're pushing in the same direction, right? So this is clockwise and this is clockwise. Now F2 is actually pushing counterclockwise tangentially to the inner rim, or rather the outer rim of the small disk. So this one's going in the opposite direction. So that's something that we need to pay attention to. So this is actually going to be what you would call CCW, counterclockwise direction, clockwise direction, clockwise direction. Okay? So we would use that to define the direction that we're having, that the torque is pushing. All right, so for the next part of the problem, it asks us to plug in numbers. Pretty much it says R is equal to 4.2, F1 is equal to 10.5 newtons. Okay, and so that means that we just plug these in. So we have 2 times 4.2 times 10.5. This is T1, and this is going to be in the clockwise direction. T2 is equal to, what do we have? I guess we don't really need to include the negative. If we just say, if we notate that it's counterclockwise, we don't need the negative. So this is going to be 4.2 over 2 times 10.5 in the CCW direction. T3 is equal to 4.2 times 10.5 in the CW direction. Okay. So plugging those in, we get 88.2 Newton meters, CW. This is 22.05 Newton meters, CCW, and this is 44.1 Newton meters, CW. Okay, and notice that, I mean, by the diagram, this one is almost twice as large as this one, and that's pretty much exactly what we get. I've notated these backwards. This one is actually T1. This is T3. This is T1. So for T3, we have 88. That's up here. This is the larger of the vectors. For T1, we have 44, which is half of F3. That makes sense by the diagram and by what we found here. This is 2RF1, this is RF1, right? Okay. But also just because, I mean, we found this and just plugged in numbers, so this makes sense more by the diagram is actually what we're looking for. And now this is a fourth, pretty much, right? So that makes sense. It looks about the same here, but what we're seeing is that this this radius is halved, right? So if this is the same as this force, like, so if we took this force and pushed it along the tangent of this disk, you would still have it by half because we are taking the radius by half. So these values make sense to me, and I believe that's it. But number 73 we can look at because this was rather short. So 73 says find an expression for total torque exerted around the center of the disk in terms of R and F1. I mean, pretty much you just have to add them up. But recall that T2 is in the opposite direction, right? So you have R over 2 F1. That's a negative direction. We have 2R F1. That's a positive direction, and then we have RF1. This is going to be the net torque. Okay, and then we say, okay, so let's just add this up. So it's 3RF1 minus R over 2F1. That gives us a value of let's just take this out. So RF1, and then we have 6 halves minus 1 half equals 5 halves. And so that's your net torque is going to be 5 halves RF1. Okay. Thanks.